Okay guys, good afternoon. So the test is tomorrow at 4. This test will start at 4 o'clock tomorrow and it will finish at 40 past 4. So you have exactly 40 minutes to do the test. It will take place in this room, okay? So please come like about 10 minutes before 4 o'clock so that we need to arrange things. Okay, so try to come to this room about 10 minutes to 4, okay? And any questions about the test, you can email me 24/7 or Zoom me 24/7, or you can see me in my room upstairs. Tomorrow I will be in from 11 to 4 p.m. So 11 a.m. to 4 p.m. I'll be in my room to answer all your questions. So feel free to drop by for all questions you have. Okay. And after the test, I will mark all your papers, and I will let you know of your mark and feedback by the evening tomorrow. So you should get an email from me by the evening of tomorrow. Yeah, not too late. Okay. And there will be a tutorial tomorrow. So let me give you the tutorial sheet. This is the tutorial sheet for tomorrow, 5 to 6. Okay. This is the tutorial sheet for tomorrow. All of you got one? Yes. Okay. Okay guys, can we get back to the class please? So last week I started talking about estimation of VAR, estimation methods for VAR. And there are 3 kinds of estimation methods: the parametric ones, the non-parametric ones, and the semi-parametric ones, right? I started talking about the parametric ones first, right? So before that these are the parametric methods, starting with the normal distribution method. In this case, the estimate for VAR is given by this, where the MLE for mu and sigma are this one and this one. Now, if you haven't taken my course last year, I sent you guys an email yesterday giving you the link for the course I taught 2 years ago, which was called Statistical Methods. This is the course number 20802, right? So if you haven't taken this course, like for example, derivations of finding the MLE for mu and finding the MLE for sigma, you need to know how to do it, right? But those are kind of stuff I taught in the course, Math 20802, right? Alright, so please, so if you haven't taken that course, please make sure that you know how to do these things. But I'm not going to explain again because these are stuff I taught a long time ago, right? Okay. Okay. So this is the maximum likelihood estimator for var for the normal distribution, right? And can be shown that the estimator is asymptotically unbiased and consistent. And once again, these concepts are defined. Unbiasedness and consistency are defined in this course, right? And then that's the normal distribution. Then I talked about the uniform distribution. In this case, the estimator for var is given by this formula. Again, these results come from Math 20802. So once again, please make sure that you do know how to derive these, right? Okay. And once again, it can be shown that this estimator is asymptotically unbiased and consistent. And the next thing is the exponential distribution. For this, the estimator for var is given by this. Again, this result comes from the material I taught in this course, right? This is the estimator for var, and it can be shown that this estimator is unbiased and consistent, right? So the concepts like unbiased, consistency, all that is once again taught in the course Math 20802. The next thing I'm going to talk about is the power function distribution. So this is number 4. Alright, this is known as the power function distribution, and if you may recall, do you guys remember the formula for var for this? In this case, we did this example a while ago. We know in this case the formula for var This is the formula for y. Okay. Now we need to find the maximum likelihood estimator of this. In order to do that, we need to find the MLE of A, right? So the likelihood, I mean, this time I'm going to explain how to derive the MLE, so that if you haven't taken the course statistical methods, you will know how to do it. Right? Remember, the likelihood function is always the product of the density function. This is the density function, which is the derivative of this. Now you can simplify this to this, and then you take the log likelihood. I'm sure some of you have done this before in statistical methods. The log likelihood is just simply the log of this, which is okay, and then you take the derivative with respect to A, the derivative with respect to A is this, and then you set this to 0 and solve for A. Now if you solve this equation for A, you will get A hat equal to minus okay. So this is the solution for the likelihood equation. Now to make sure that this is a MLE, you need to take the second order derivative. So let me put this over here. Can you see this, guys? Yeah. The second order derivative is, this is, sorry, let me know if you can't see the screen. Can you see it now? Oh, you can. Okay, the second order derivative is this, and this is of course negative all the time, hence okay, do you see what I've done? I mean, this is I mean, if you have taken the course statistical methods, this is pretty straightforward for you. Now this must be straightforward for you. So this is how usually you find the maximum likelihood estimator of a parametric distribution, right? So in this case, the MLE for A is the one given over there, right? This is the MLE for A. Okay. So once again, I send you guys the link. The link yesterday I sent you an email giving you the link for statistical methods. So if you haven't taken that course, please make sure that you are familiar with the contents of the link. Okay. So hence, now the var, as you know, the var is this one here. This is the var. So the MLE of var will be this, okay? Or in other words, it will be, we can also write this like P 1 over m times the sum of log of xi. Okay, so this is the maximum likelihood estimator for value at risk. Okay, it can be. All right, I will leave it like this for the moment. Okay, that's number 4. Okay. Now number 5. Come on. Number 5 is known as the, so we've done 4 estimation methods so far under the parametric family. Number 5 is the variance, is an important method. It's known as the variance covariance method. Okay. Now in this case, not P, I mean, let me use some other letter, not P, maybe, let me use M, maybe M. This is M. Okay, suppose you have a portfolio that is consists of M independent investments. Okay, let Xi denote the investment on, the loss on investment I, and let omega I denote the weight, because certain investments may be more important than others, right? So let omega I denote the weight on investment I. Okay. Then you understand what I'm saying? So you have a portfolio that consists of M investments. Xi is the loss on investment I. Omega I is the weight on investment I. Because certain investments may be more important than others. So that's why you give a weight. So in this case, the total portfolio loss can be written like this. It's a sum of omega I times xi I from 1 to n. Okay? Okay? Okay, suppose xi, suppose the xi being the loss on investment I as the normal distribution with these parameters, right? Then what can you say about the distribution of x? I mean, if you've done statistical methods, you will know the answer. What is the distribution of x? It will be normal 2 with parameters Do you know this result, guys? Don't tell me you don't know. I mean, well, if you don't know this result, please look at the link I sent you yesterday. If you look at the link, it shows you how to prove this result. I don't expect you to know the proof, but if you want to know how to prove this, just look at the link I sent you yesterday. Okay? All right? Okay, guys. Now, okay, so this is the distribution of the total portfolio loss. Now we are interested in finding the VAR, right? So set the reason I am doing this is because I want to find the value at risk of x. X is the variable of interest, which is the total portfolio loss, right? Now, what is the CDF of x, guys? It will be phi Alright, this is so what I have written here, guys, this is the CDF, or the cumulative distribution function of x, right? Okay. Now, if you solve this equation for x. This is what you will get. You will get x equal to okay. So this is, so therefore the formula for var is equal to right. So the value at risk, the value at risk of the total portfolio loss is given by this formula. Okay. Is there any questions so far? You guys okay? All right. Okay. Now what we need to do is we need to be able to estimate this formula. In practice, we don't know these parameters. We don't know what mu I is. We don't know what sigma I is. So we need to estimate these parameters, right? So that's what I'm going to do next. Okay. Suppose right, so what I'm assuming is that we have, remember, x1 to xm are the losses on the m investments. So let's suppose that we have this data. These are data on x1, and these are data on x2, and these are data values on xn, right? Okay. There's no need to copy. I will just scan it after the class. All right, for those of you who've done statistical methods, can you tell me what the answer is? Okay, given this data, given all this data, what is the MLE for mu I and sigma I squared? Yes, my friend. You okay? You remember you should done the course. The MLA for mu I will be 1 divided by alright, this will be the, I mean, again, this goes back to what I mean, statistical methods that are, and the MLE for sigma I squared will be the following: 1 divided by okay. Okay, so these so this is the MLE for the mu I, and this is the MLE for sigma I. Sorry, I forgot to put the hat. There should be a hat here. Okay. Alright, once again, I mean, if you want to know how to prove this, you just look back on the link I gave you yesterday, right? If you want to know how to prove these things. Alright, hence, the MLE for var So this is the formula for computing the value at risk when you have a portfolio of losses and you are interested in the total portfolio loss. I mean, most companies they are interested in the total portfolio loss. So this formula here is very useful, right? Provided that the individual losses, the individual investments, the losses on the individual investments are normally distributed. If that is the case, then you can use this formula to compute value at risk for the total portfolio loss, right? Okay. Okay, guys. Any questions, guys? Let me know, guys. Please. The next thing. So this is number 5. Is it number 5 or 6? 1, 2, 3, 4. 4. Okay, number 5. This is estimation method number 5 under parametric assumptions. 1, 2, 3, 4. Yes. Number 5 is the Weibull distribution method. Okay. So this this CDF here is known as the CDF of the Weibull distribution. If you haven't come across this before, this is the CDF of the Weibull distribution, right? This okay. Now we are interested in var. All right. So we want to set equal to p, which implies this, and this implies that is this. Take the logs both sides, you get okay, and therefore var. Oh, let me do it one more step. X is equal to this, right? And var is equal to so this is the formula for, so this is the formula for var if the data on the losses follow the Weibull distribution, right? And here we have two parameters, theta and beta. So for this formula to be useful, we need to estimate these two parameters, right? So that's what I'm going to talk about now. I don't expect you to know this proof of this, but it can be shown that theta hat and the beta hat are the solutions of the following. The first one Sorry, this should be beta hat, not beta. This is beta hat. Alright, it can be shown that the theta hat and the beta hat are the solutions of these two equations, where x bar is the sample mean and s squared is the sample variance. So let me write that down, where x bar is the sample mean and s squared is the sample variance, which is, so you have, when I say sample variance, you need to divide by n minus 1, not n. Okay. Anyway, you don't need to know the proof of this, but if you can prove it, that would be good. Right, so it's basically these two equations will need to be solved numerically, because there's no closed form solutions for theta hat or beta hat. So you will need to, especially the first equation, you will need to solve it numerically, and once you get the solution for beta hat, then sub it in here to get theta hat. Right? Okay. Alright. Okay. Alright, so those are, so we have done so far, just to summarize, we have done five different parametric estimation methods for computing VAR, or value at risk, right? The next thing on the list is non-parametric estimation method. As I said before, non-parametric, had you guys done non-parametrics before? Yes, no? Why you're keeping quiet today? Huh? Did you guys done non-parametrics? Anyone? Yes? So non-parametric means is you don't assume any particular distribution for the data. So the data, you treat the data as itself, right? Without assuming that it follows any particular distribution, right? So I'm going to talk about, where am I? I'm going to talk about non-parametric methods, starting with number one. So, okay, B. Non-parametric estimation methods for what? One. You guys okay? Number one is known as the historical Okay, the first method is known as the historical method, right? The historical method is a really simple method. All you have to do is the following. So you have data Right? Arrange the data from the smallest to the largest. So what I mean by that is the following. So this guy here, this is the smallest data, and this one here is the largest. Right? Then the value at rest at P is equal to x sub I in brackets if P belongs to the interval from I minus 1 divided by n to I divided by n. So this is the, you see, it's very simple. This is, oh sorry, it's still hidden. Oh. The formula for computing var under the historical method is this one here. So you estimate var at P as the ith order statistic. I mean, this is the first order statistic, this is the nth order statistic, this is, and so on. This is the second order statistic. And you estimate it as the ith order statistic if P belongs to this interval. Does it make sense or not? Yes? No? Anyway, I will do a couple of examples now. Let's see. Let me see. Let me do 2 examples, then it may make it clearer. You speak to me, guys. Seems that you seem tired today. Why? Example 1. Suppose we have data from 5, minus 2, 3, 0, 1. So suppose, I mean, these are some imaginary data I created, alright? So these are, suppose these are the actual losses, alright? Okay? Now, according to the historical method, the first thing you must do is to arrange the data. Now, what's the smallest? What's the smallest of this data? Come on, talk to me, guys. What's the smallest of these data? Minus? And the next one? The next one? The next one? 3. The next one? 5. So this is your x sub 1. This is your x 2. This is your x 3. This is your x 4. And this is your x 5. Now, if I ask you, what would this, if I ask you what is var at 0.4, what do you think that would be? Just use the formula, guys. This is the formula. The formula I gave you is over here, guys. This is the formula I gave you. Right? var is equal to this if P belongs to this interval. Right? So if P is 0.4, where would it go? What would I be? Can I be equal to 1? What about 2? Yes. So what's the second? So the answer is what? 0, right? Is that clear how I got it? We just try different values of I. Put I equal to 1. I equal to 1 does not cover 0.4, right? Because n, remember, n is the sample size, which is 5. So if you put I equal to 1 into here, this will be 0. This will be 1 divided by 5, which is 0.2. Yeah? So it will not cover. But if you put I equal to 2, this will be 0.2, and this will be 0.4. So this will cover. So the answer is I equal to 2. So I equal to 2 is 0.0, right? So that's the. All right. Let's do another example. Var 0.9x. What do you think this would be? 0.9. Because if I is 5, then we have 4 divided by 5, which is 0.8, and this is 1. So 0.9 is between 0.8 and 1. Right, so the answer is 5. Okay, so the historical method is a very simple method. It's a very easy method to compute value at risk, right? Anybody can do it, right? Okay. So there, we are done with that. Okay. The next one. That's number 1. Number 2. Bootstrap is a resampling method. I don't know. Have you done Bootstrap before? Yes. Yeah, Bootstrapping is a resampling algorithm. Was developed by Brad Efron, who's a professor at Stanford University in the U.S. So it's been around for a long time. Okay, so the thing is, all right, suppose it works like this. Suppose you have the data. So the data on losses, which is say x1 to xn. Okay, sorry. I'm sorry. Let me start again. I shouldn't have put this column. Sorry, I just made a mistake in the. So the data on losses is x1, x2 up to xn. Okay. The first thing you need to do is to Do you guys know what the empirical CDF is? It's defined by this, right? And if you draw a picture of it, it will look like a staircase. So let me try to draw a picture. I'm not good at all in drawing anything. So it will look like this will be your. Alright, let me. This is your x-axis, and this is your f hat x-axis. Okay. And this will be the smallest data, which is x sub 1, and this will be the second smallest data, which is x2, and so on until you hit this point here. This will be the largest data, x sub n. So this will be 0 here, and this point here, this will be 1. Okay, so this point will be 0, this point will be 1. Okay, and it looks more or less like a staircase. Now I will take a 10 minutes break now. After that I will explain how the bootstrap works. You might have seen this before in other courses. Have you seen this? No? Come on guys, talk to me guys. You haven't seen this before. Empirical CDF. You have? So good. Alright, I'll take a 10 minutes break now, and if you have, after that I will start again. If you have any questions on the test, you can ask me, or any other question. Do you have any questions for tomorrow? Test. No. What about you, man? All right. You revised already?
Yeah, I have. Tomorrow, right? It's gonna be based on chapter 1, isn't it?
Yeah.
Chapter 1, just minutes.
Yeah. It's only the form. Did you look at the formula sheet? And see the only goes tomorrow.
That was like 2015 if you know.
This is about showing the same domain.
Yeah.
Yeah, look at the solutions. And the solutions are online.
I don't think there's a link for 2015. I don't know.
Do you have any questions for tomorrow?
Yeah, I guess it's probably was called the example. Yeah, that's what it is. You go for that. Really? So he that's funny. But he started with the first one, like with manual. So he did.
对啊，经常打啊，官网也是，他每一次都能。公交的，今天打的，真的打啊！我打电话去那个他就在他那个在那个不你官网也打，真的好。
They know that something good.
就是这个鬼，他们说还是航海这个地方。哎，你其他黑五真打的，黑五也打了，黑五肯定打，但是你去国内你其他的打，他很少打。你去他就是你想要一个勾粉。这个这我们还是拍啥推下去了。这不用了。
分给澳洲。Saturday night, oh my god. Saturday night. I don't know if it's called never. think I was an Irish then going to have walking. Huh? We walked from Leiden to during April, May, right? During exam season.
You guys okay? Yeah. So the method for computing the value at risk under the bootstrap method goes like this, right? So that's the slide where I describe what f hat is. F hat is the empirical CDF, right? And there are routines in R. I'm sure you're familiar with R for computing f hat. There are also routines in R for simulating from f hat, right? So the first step is to simulate B independent random samples, each of size n, from f hat, right? And you can do that using R, right? So B could be any number, like it could be 100,000, 10,000, or million, right? So second step, are you guys listening or what? The second step is to compute var by the historical method, which I have already described, for each of the B random samples. So if B is 100, for example, you have 100 different estimates for var. B is 1000, you have 1000 different estimates for var, right? Okay. And the final step take the final estimate for var as the mean of these. Alright, so the final step says the following, that take the final estimate for var either as the mean or the median, of the values obtained in the second step. Remember, the second step computes the var for each of the B random samples, right? So you have B different estimates for var, and the final step says take the final estimate for var either as the mean or the median of the estimates for var. Right. Okay. Any questions so far? Imam, okay? If you have any questions, let me know, guys, please. So that's the bootstrap method. The next one is known as is connected to the bootstrap method. It's known as the jackknife method. Okay. So once again, suppose you have a data set on losses. So x1 to xn. Okay. And the jackknife methods works like this. Okay, the first step is to compute the value at risk by the historical method for the data from x2 to xn. So what I have done here, I have excluded the first data point, x1. Right? So I've removed the first data point and consider the remaining data. Right? And for the remaining data, I compute var by the historical method. Right? And the second step okay. So in the second step, you see what I have done. I have considered this data. I have removed the second data point. So the data that we consider here is x1, x3 up to xn. Right? And you do that until you keep doing this until the last step would be to compute okay. In the last step, we compute the var by the historical method for this data. So in this data, I have removed the last data point. So you have x1, x2 up to xn minus 1. The last data point has been removed. Right? And let this denote the historical estimate. Right? And the final step is the following. Take the final estimate for var as the following, as either the mean, so either the mean or the median so this is the mean and the median is okay, this is the median. Okay, so this procedure is known as the Jagnath procedure for estimating value at risk. This is clear, guys, or not? So is this procedure clear to all of you? Yes? No? Let me know if you have questions. So basically the idea behind this is to use the historical method to estimate var by deleting one data from the original data. So by deleting one observation from the original data set at a time. So you do that n times, right? So after doing n times, you get n different estimates for var. So the final estimate for var is either the mean or the median of the n different estimates. Is that right? Okay. Okay. So this is the jackknife method. Number 3. Number 4. Number 4 is known as the kernel method. Do you know what kernel estimation is? You might have done this. Do you know what a kernel is? No, you don't know. You probably did it in some other course. Did you guys do that? No? Oh, come on. Why you keep saying no all the time? All right. Suppose you have a data on losses, say x1 to xn, right? H, this is H, okay. I hope you can read my handwriting. If you can't read my handwriting, let me know. H is the bandwidth, and G right? So this, so if you don't know what the kernel CDF is, this is the formula. I don't know whether you've seen this before or not. You might have seen this, I don't know. This is known as the, if you have a data set, right? If you have a data set, the kernel CDF of the data is defined by this equation here, this equation, right? Where H is the bandwidth, G is the integral of K from over this range, and K is known as the kernel PDF. And the kernel PDF is usually chosen to be the normal PDF, the standard normal PDF, which is this one. I'm sure if you know what this is, the standard normal PDF, right? Okay. and H controls the smoothness. The reason that's known as the bandwidth is because it controls how smooth the kernel estimate is. If H is small, then it will be like ziggy. If H is large, it will be more like smooth. Right? So H controls the smoothness. Okay. So the larger the value for H, the smoother the estimate will become, right? Okay, all right. So that's that. Now I'm not done yet for this FFAT. The we want to know how to compute VAR, right? The VAR can be the VAR can be computed as the root. I'm sure you know the term root from mathematics. So as the root of this equation, if you're familiar with R, there are functions in R that can compute the root of an equation. Like for example, uniroot. There's a function called uniroot that can compute the root of an equation. So if you have this, if you program this in R, you'll be able to find the root, and that root will be the estimate for VAR. Okay. Okay. Alternatively, you can estimate VAR by the following. This is a big equation, so give me a sec. Okay. All right. So there are two formulas. So under the kernel method, you can use two different ways to compute var. One is to use to find the root of the equation fx equal to p, and that root will be the var, estimate the var. The second, if you don't like that way of doing it, you can use this formula here, right? You can use this formula. That will also give you an estimate for var, right? Okay. So either way is fine. That's the kernel estimate for var. You have any questions so far, guys? Any questions so far? Let me know. All right. The next thing I'm going to talk about. So far we talked about 5 or 6 parametric estimation methods and 4 non-parametric estimation methods. And the next thing I'm going to talk about is semi-parametric estimation methods. So this is C. Semi-parametric estimation method, right? Okay. Now, in this, semi-parametric means that it is a combination of the two. It's a combination of parametric methods and non-parametric methods. So there are elements of these methods which are parametric, and there are elements of this method which are non-parametric. That's why it's known as semi-parametric. Now this is where what we did long time ago comes back. You may remember these pictures from million of years ago. Trying to find it here. Here we are. Do you remember this picture? Do you remember this picture here? Right? This is, what is this known as? This is what definition 1 of extreme values, right? Yeah, where you have a large data set and you only pick the only one data point, right? Which is the largest data point, right? Okay. Now, so I'm gonna use this. The first method. Okay, let me put it here. Hopefully you can see this, right? The first method is known as the GED method for obvious reasons. Okay. So you have if right, which is what I meant here. The largest data point is the extreme value. Do you guys remember this formula here? What is this known as? Do you remember this formula? What is the name of this formula? Come on, guys. You don't remember what is this known as? It's the CDF of the GUV distribution, right? Yeah, we did this long time ago. You forgot already? Come on. I thought you know. Okay. Now, to find we want to find the value at risk. Okay, to find the value at risk, we need to set the CDF equal to P and solve for X in terms of P, right? Okay, so this implies that this implies this, and this implies, let me do this quickly. If I make a mistake, please let me know. This will be equal to X equal to mu this, correct me if I'm wrong, I think this is what I'm getting if you solve this. So var, so what this implies is that var equal to this, right? So do you follow what I've done, guys? What I have done is to set the CDF of the GUV distribution equal to P and solve for X in terms of P. And if you do that, you will get this as the formula for var. Okay? Okay? Right. Now to estimate var, there are three parameters we need to estimate. All right, the mu, the sigma, and psi. Now, what I'm going to do is the following. To estimate psi, I'm going to use I'm gonna estimate the parameter psi using a non-parametric method, right? Which is known as the Hills estimator. First, what you do is the following. guys okay? Are you tired or what? Come on, guys. So you estimate the parameter psi using one of these formulas. Now, if you look at these formulas, right, we are not making any assumptions about the data following a certain distribution, right? These are both non-parametric estimates. So this is a non-parametric estimate for psi, and so is this one, right? Now, remember MLEs are by definition, MLEs are parametric estimates, because when you compute an MLE, you are assuming a certain distribution, right? So when you say MLE, it's automatically a parametric estimate, right? So I've taken mu hat and sigma hat as the MLEs that we talked about earlier in the course, right? If you look back at the notes for G, you will know what these are. And I've taken psi hat to be the non-parametric estimate. So hence, just to finish off, just give me a sec. Just to finish off, hence, alright guys, so I hope you understand what I have done. So this formula here is an example of a semi-parametric estimate of Y, because I'm combining parametric and non-parametric estimates. In particular, psi, the parameter psi is a non-parametric estimator, right, psi hat, whereas mu hat and sigma hat are parametric estimators, right? Hence, this formula here is a semi-parametric estimator, because you're combining the two. Okay. All right, guys. So good luck tomorrow. But if you have questions, I'll be awake all night. If you have any questions, you can email me. All right. And tomorrow I will be in my room from 11 to 4 p.m. You know my room, right? You know where I am. I know some of you haven't been to my room. I don't know where. I hope you find where my room is.
Okay.
You know my room.
Yeah.
Okay. Yeah. So any questions? Just come to my room or email me 24/7. That's it. Are you working on what are you working on right now? I've got some ideas, but I don't want to give it to you now because you're missing the work. I will keep after you finish it. I will give you
3, madam. If I is 3, then we have. Can I have a pen? Can I have a pen on paper? Can I have a pen right here? If I is 3, if I equal to 3, then you have 2 divided by 5, open bracket, and 3 divided by 5, close bracket, is close bracket. So 2 over 5 is what? 0.4. 3 over 5 is 0.6. So this does not contain 0.4 because this is an open interval. You understand? So it doesn't contain that. Yeah.
There are n systems, and each of these systems are alpha.
Yeah. Well, this is a little difficult. This question is really difficult.
And
So the thing is, this is the geometric distribution, right? N equal to, so this is what it says. N is a.
so we should use the total probability.
No, not total probability. No, it's not. It doesn't use the total probability. No, it's different from that. You have to think about it. N is the N systems are functioning, right?
It's a random.
N is a random variable, right? Following the geometric distribution.
Yeah.
And suppose too that the system is made of alpha parallel units. So the system will fail. Okay. Is that one independent exponential random variables with probability, density